Up to this point, we have seen how to find a line of best fit for particular data sets, and we have been looking at two methods. The first method we used was the intuitive approach of visually fitting a line to a scatter plot of the data. We augmented this visual fitting process by utilizing criterion functions that we could calculate for each candidate line and use for finding the line that optimizes that criterion. We considered three different criterion functions in this approach. First, the number of points that a candidate line goes through. Second, the sum of the absolute errors, or SAE. And third, the sum of the squared errors, which we abbreviate by SSE. We then turned our focus to the SSE criterion and used that criterion function to identify a system of equations called normal equations, the solutions of which are the estimators that optimize, in this case minimize, the SSE criterion function. These estimators are called the least squares estimators of the beta parameters, and we have seen how to find their values for given data by plugging in summary statistics for the data and then solving the system of equations for the values of the least squares estimators. In this lecture, we derive formulas for the least squares estimators of the beta parameters in that simple linear regression model, which can then be applied to any given bivariate data set. These formulas are derived from the normal equations by symbolically manipulating the normal equations so that we can algebraically solve them in terms of the least squares estimators. So let's take a look at the derivation. As we have shown previously, the least squares estimators of the beta parameters in the simple linear regression model are values beta 0 hat and beta 1 hat that satisfy the system of equations shown below. This system is called the system of normal equations. Formulas for beta 0 hat and beta 1 hat can be found by algebraically solving this system of equations for the estimators in terms of the notation for these summary statistics rather than in terms of the observed values of the summary statistics, which we have done when solving this system for a particular data set. As a first step, divide both sides of the first equation by n. This gives the equation shown here, beta 0 hat plus the product of beta 1 hat times x bar, and that sum has got to equal y bar, the average of the response variable. Note that since the least squares estimators beta 0 hat and beta 1 hat must satisfy this equation, it follows that the least squares line always passes through the point x bar, comma y bar. Solving this equation for beta 0 hat gives the expression beta 0 hat equal to y bar minus the product of beta 1 hat times x bar. So we have a formula here for beta 0 hat in terms of beta 1 hat. Once the value of beta 1 hat has been obtained, it can then be substituted into this formula and beta 0 hat can then be calculated. To find a formula for beta 1 hat, we substitute the expression for beta 0 hat found on the previous slide into the second normal equation. This gives the equation shown here, which we can then solve for beta 1 hat. And when we do that, we get this formula for beta 1 hat in terms of the summary statistics for the data. So the formulas for beta 0 hat and beta 1 hat are given by the following. And just note that procedurally we would first calculate beta 1 hat because it's expressed exclusively in terms of the summary statistics for the data. And then once we have beta 1 hat, we can then calculate beta 0 hat. Now at this point, it will be helpful to introduce notation for what we might call the intermediate summary statistics that are used in the calculation of beta 1 hat. In particular, let's let S sub xy be the expression in the numerator for beta 1 hat. And so we can see here that S sub xy is defined to be the sum, I going from 1 to n, of the products x times y minus n times x bar times y bar. And note that we can re-express that as the sum of the products of the x times the y's minus 1 over n times the sum of the x's times the sum of the y's. Now, it may not be clear, but this is actually a shorthand or computational way of expressing the corrected sum of products for the x's and the y's. Similarly, let's define the quantity S sub xx as the sum of the squared x values minus n times the square of x bar, and that is algebraically equivalent to the sum of the squared x values minus 1 over n times the square of the sum of the x's. And again, it may not be clear, but this is actually a shorthand or computational formula for the corrected sum of squares of the x's. So using the notation S sub xy and S sub xx, the formula for beta 1 hat can be written in the more simplified form shown here. Beta 1 hat equal to S sub xy, which again is the corrected sum of products of the x's and the y's, divided by S sub xx, which is the corrected sum of squares of the x's. And as I show here on the bottom of this slide, again, S sub xy is the corrected sum of products of the x's and the y's, and S sub xx is called the corrected sum of squares of the x's. And so the formulas for beta 0 hat and beta 1 hat can be expressed in terms of this more concise notation. Beta 1 hat equal to S sub xy divided by S sub x. And then once we have that, we can plug that into the formula for beta 0 hat. So beta 0 hat being equal to y bar minus the product of beta 1 hat times x bar. And note that this can be re-expressed in terms of the sums of the x's and the y's as 1 over n times the sum of the y's minus S sub xy over S sub xx times 1 over n times the sum of the x's. So the formula that you use will depend in large part on the summary statistics that you have at your disposal. Now, while we're at it, it will also be useful to define the following notation. So this is analogous to S sub xx. Okay, this is the formula for the corrected sum of squares of the y values, and we're going to denote this by S sub yy. So this is given by the sum of the squared y values minus the sample size n times the square of the mean of the y values, and that's equal to the sum of the squared y values minus 1 over n times the square of the sum of the y values. And again, this is a simplified formula or computational formula for the corrected sum of squares of the y's. Now, we're going to make use of this expression, this quantity, when we calculate the estimator of sigma squared, which you'll recall is the variance of epsilon, the model error term. So let's apply these formulas to the rocket propellant data. This is example 2.1. And so we have here the data set that we looked at in a previous lecture video. And here are the basic summary statistics that we'll need to calculate the least squares estimators using the formulas. So we have the sample size of 20. The sum of the x values is 267.25. The sum of the squared x values, 4,677.6875. The sum of the y's you see here, 42,627.15. and then the sum of the x's times the y's. Let's see here, 528,492.6375. All right, so let's calculate first S sub xy, the corrected sum of products of the x's and the y's. And so plugging the needed summary statistics into this formula, we see that the corrected sum of products of the x's and the y's is equal to negative 41,112.65438. All right, and so notice that I'm including all of the decimal places here in the display. When we're doing these calculations, because we're doing we're calculating these intermediate summary statistics that we're then going to use to calculate, for example, beta 1 hat, we always want to use the full precision available to us. And the best way to do that is to just do all the calculations internally in the calculator. So instead of calculating, for example, S sub xy, writing it down, calculating S sub xx, writing that down, and then re-entering those values by hand, the best way to do it, if possible, and it really is possible with modern calculators today, is to just do all of the calculations in the calculator itself. So really the only thing that we should ever have to enter by hand is the raw data. Okay, so we could do this calculation on a calculator. For example, I'm using the TI-84 calculator. I could then calculate S sub xx, okay, and the calculation is shown here. And so again, plugging the needed summary statistics into this formula, we see that the corrected sum of squares of the x's is 1,106.559375. So I've got both of those results in the calculator, and I can just, if you'll remember, I can just arrow up and grab the numerator value, the negative 41,112.65438, press enter, then press the divide key, and then again arrow up and get the value for S sub xx, press the enter key, and so we're basically copying and pasting those values into the current calculation. And regardless of what's being displayed on the calculator screen, when we do that, when we copy and paste those values into the current command line, it's using the full precision of those values as they are stored in the calculator memory. All right, and so if we do that, if we always use the most precision possible by doing the calculations in using the values as stored internally in the calculator, then we're going to minimize the rounding error. So when we do this calculation, we see that the least squares estimate of beta 1 hat is negative 37.15359,095. Now that we have beta 1 hat, we can plug that into the formula for beta 0 hat, and because the summary statistics that I displayed were in terms of the sum of the x's, the sum of the y's, as opposed to their means, I'm going to use this version of the formula to calculate beta 0 hat. So it's equal to 1 over n times the sum of the y's minus beta 1 hat times 1 over n times the sum of the x's. Plug those values in, and we can see here that I get a least squares estimator of beta 0 hat equal to 2,627.822359. So the least squares estimate of the simple linear regression line is y hat equal to, and then the form beta 0 hat plus beta 1 hat times x, and that's equal to the line 2627.822359 minus 37.15359,095 times x. Now note also that once we have this prediction formula, this estimated regression line, we can calculate the predicted values of y at each value of x. All right, so we can calculate the y hats, and once we have done that, then we can take the difference between the observed values of y, the actual y values themselves, and the predicted values, the y-hats, square those differences, add those squared differences up, and that will give us the SSE for the least squares line. And for this situation, for this least squares line, the sum of squared errors, the SSE, is equal to 166,254.8581. Now recall the values of the least squares estimators that we obtained by applying Gaussian elimination with Jordan reduction to the augmented matrix corresponding to the normal equations. And so we did this in a previous lecture video, and when we did this, we found the least squares estimators of beta 0 hat and beta 1 hat from the reduced matrix, and we found them to be beta 0 hat equal to 2627.82236 and beta 1 hat equal to negative 37.153.59094. And so the values of the least squares estimators obtained using the formulas are essentially the same as those that were obtained by directly solving the normal equations using Gaussian elimination with Jordan reduction. The only difference being in the last displayed decimal digit or decimal place of beta 1 hat, and this is due to the difference in rounding errors associated with the two different methods of calculation. Okay, next let's go back and look again at the example that we called example 2.0. And so here was the data set for this example. The basic summary statistics that we need to calculate the least squares estimators using the formulas are given here. And so the sample size for this data set is 10. The sum of the x's is 5.4. The sum of the squared x's is 3.84. The sum of the response variable y is 5. And the sum of the uncorrected products of the x's and the y's is 3.44. All right, so let's first calculate the corrected sum of products of the x's and the y's, S sub xy. And so plugging in the values of these summary statistics in this formula, we get a value for S sub xy of 0.74. Then we calculate S sub xx, the corrected sum of squares of the x's. And so we plug in the values of the sum of the squared x values, the value for n, which is 10, and the sum of the x's, and we get a value for S sub xx of 0.924. And then once we have those values, we have all we need to calculate the least squares estimator of beta 1 hat, and that turns out to be 0.800.865.8009. And then finally, once we have beta 1 hat, we can plug its value into the formula for beta 0 hat. And so doing that, along with plugging in the other necessary summary statistics, we get a value for beta 0 hat of 0.0675324675. And so the least squares estimate of the simple linear regression line is y hat equal to beta 0 hat plus beta 1 hat times x, which is equal to the expression shown here with those values for beta 0 hat and beta 1 hat plugged in. Again, once we have the least squares estimate of the simple linear regression line, we can evaluate that line at the values of x in our data set, and that will give us the predicted value of y for each observation in our data set. It will give us the y hat values for each observation in the data set. We can then subtract those predicted values from the observed values of y, square those differences, add those squared differences up, and that will give us the sum of squared errors, the value of this criterion function for the least squares line. And that turns out to be, in this case, 0.34735.93074. Now recall our visual model fitting efforts that we did for this particular data set in a previous lecture video. All right. Next, let's do the same thing using the sum of squares error as the criterion function. And so we start off again with our candidate line being horizontal with an intercept of 0.5, which is the mean of the response variable. We could start it off anywhere, but this is just where I happen to be starting this. And so this time what I'll do first is I will decrease, well, that's not what I wanted. I'll decrease the intercept, right? We know that it's going to have to intercept down here somewhere less than 0.2, it appears. And then I'm going to, from there, increase the slope. And we can see the value of SSE decreasing as we bring this line more in line with the data. Okay. And so let me go back up here to the intercept. I can see that I need to decrease that a little bit. So that looks like it might be about right. And so now let's keep our eye on SSE. All right, so I'm going to increase the slope a little bit, and that did decrease the SSE. All right, continuing to increase that slope, and if we look at the graph visually, it does look like it needs to increase a little bit. And so let's keep doing it. Let's keep our eye on the value of SSE. Okay, so when I'm at 0.8 for the slope, we have an SSE value of 0.3474. If I decrease the slope, that increases SSE. And if I increase the slope from 0.8 to 0.81, that also increases the SSE. Okay, so it looks like the best fitting line according to the SSE criterion has an intercept of 0.07 and a slope of 0.8. So let me go ahead and enter those values. In finding the best fitting line in terms of SSE using our visual fitting approach, we came up with the line that has parameter values beta 0 hat equal to 0.07 and beta 1 hat equal to 0.80. These are consistent with the values we obtained using the formulas beta 0 hat equal to 0.067532465 and beta 1 hat equal to 0.80086580009 when we round those to 2 decimal places. In addition, the SSE for the least squares line found using the formulas, which was 0.34735,93074, when rounded to 4 decimal places, is equal to 0.3474, which is equal to the value of SSE for our visually fitted line. So I'd say we did a pretty good job of visually fitting the line in this particular situation, at least. Having said that, I think you would agree that there is a limit to the precision we can obtain in the estimates, at least in terms of the time it takes, and also the patience we have to have in performing that visual fitting process. In addition, as I indicated previously, the visual fitting process does not scale well as the number of variables in the model increases. This is true for both the number of explanatory variables as well as the number of response variables. So while the visual fitting process has value as a teaching concept development tool, it's not a tool that would be efficient enough or accurate enough for practical use. The good news is that the approaches for finding the least squares estimators by 1. Numerically solving the normal equations to find their values, and 2. Algebraically solving the normal equations to obtain formulas for the least squares estimators, both scale very, very nicely even as we increase the number of explanatory variables. In addition, by finding formulas for the least squares estimators, we will be able to go beyond just calculating the values of the least squares estimators. We'll be able to uncover information regarding their sampling distributions, both their joint and marginal distributions, that will allow us to go even further and develop procedures for making additional statistical inferences about the model parameters. And this will include testing hypotheses about the parameters and also constructing confidence intervals for individual parameters, as well as confidence regions for 2 or more parameters simultaneously. I'll see you in the next lecture video.